Hello everyone, welcome to the last laboratory session on product dissection. So we will not be having any more product dissection exercises. This is going to be the last product. So this is the 10th product that we are doing. So far we have done many products, and this product is a monoblock pump. Most of you are familiar with pumps, basically to pump water or liquid or solid. We can use semi-solid, we can use pumps. Basically it will take the input from a lower head and then deliver it at a higher head. That is basically a pump. So this exercise we are doing in order to do something called the concept capturing. Okay, actually you have been doing this concept capturing in all the exercises. Knowingly or unknowingly, you are looking at how a particular product is providing a function. So that the physical form of that product actually is a concept provided by the designer. So we'll look into more details, because now you know what is a concept, what is how a concept is developed, and what are the ways in which you can actually have concept variants. So here in this exercise, what we will do is we will look into the product and then identify the parts and assemblies, and then see what particular concept is employed by the designer in order to achieve a function. So that is what actually we will be looking. Earlier we were looking at, okay, what part is providing a function. Now we look at, okay, what is the concept that he is employing. Suppose there is a transmission. So whether the transmission is through a direct contact or through a belt or through a shaft or some other methods he is employing. So that is basically a concept. So this exercise will help you to know how to capture the concepts from a product. So any product you would see and you would open it up, you will see that some specific concept the designer has employed. So what are these concepts and how these concepts are actually used in achieving particular functions can be understood through this exercise. So that is the purpose of this exercise. Okay, so the objective almost remains same, but here you identify the useful concepts employed by the designer, and then see how this concept or what kind of concept variants are existing for the same application. Designer has done some used a particular concept, but then through the previous exercises and then your exposure to the products, now you know that that can actually be done in a different way also. So what is that alternate concept that you can employ that also can be discussed in the reports. So identify the useful concept that he has employed in this particular product, and then see what kind of variations are possible in order to develop similar product. So that is also an objective of this exercise. So the monoblock pump we are using is shown here. So this is again an Usha mic, and it's a high lift model. So that is the pump you can see. So you can see there is an electric part. You can see there is an electric supply, and then there is a motor, and there is a pump body, and then you have this assembly over here which will take input and then deliver the outputs. And the mechanism wise, it is not very complex. It's a simple mechanism, because what you need is to rotate an impeller and then take the liquid inside and then deliver it outside by increasing its kinetic energy and delivering it at a higher head. So the mechanism wise, it's not very complex, but you will see that the concepts that people are employing in order to get this very interesting. So we'll look into that in the exercise and then try to identify the concepts. Okay, so there are many functions to be achieved in order to deliver the liquid at a higher head. So that is primarily the function is to deliver a liquid or a solid at a higher head. That is the purpose of a pump. Now this particular pump, if it is used only for the liquid, then it's only the liquid can be used, but there are motors which can actually use semi-solid like cement and other things also can be pumped. Okay, so there are many things that you need to generate a suction head, you need to increase the pressure at the delivery, and you need to create a particular flow rate, and you need to control the backflow and other things, and something called priming may be required. That is in some cases, not all pumps need, but most of the pump requires some kind of priming. So that is also to be achieved in the product, and then mounting and then securing the pump to prevent vibration and other things. So these are the things which need to be satisfied in the product in order to get the main function of pumping liquid at a higher head. And as usual, we will go for the procedure. Most of the initial procedure remains same, and then the what you need to do is write function to component matrix. So now this you might have done earlier also. So earlier what we used to do was part to component you used to part to function you need to map, and here you can actually do that function and the component the same way. You can actually look at the function and then see which component is providing that function, and then you will see that a particular concept is employed in order to get that particular function. So that is where actually you identify the concept employed for achieving that function. So what is the concept employed? So more than looking at the part or the component in that product, you look at, okay, what is the concept he has employed? So what is that concept, and then identify those concepts and write down the main concepts used for the function. So finally you need to, in the useful concept, you can say what is the function and what is the concept that actually he has employed to achieve that particular function can be mapped. So that way you will be able to identify all those concepts employed in the product, and some of them will be useful for you in the future design of products. So that is where actually we will try to identify all the useful concepts, and this will actually help you to develop a repository of concepts which can be used in product design at a later stage. When you want to design a product, maybe not exactly a pump, but you may be doing something else, and then you will be able to see that, okay, in this particular product, in order to reduce the vibration, they have used a particular concept. So probably that concept you may be able to use it in a different product. So that is the way you should look at this exercise. So it's not exactly to look at what is the concept that can be used for pump. The purpose is what are the concepts available in this design and which can be useful in many other fields also. So that way you look at it and then identify all the concepts and then prepare the report and submit. The report format as usual will be the same for the first part, and then the second part you will be identifying the useful concepts and then recording it. So this is what is expected from you in this exercise. I hope you will enjoy this, and the TA will be showing you all the videos, the video of product dissection and identifying the parts, and then they're looking at their functions. I hope you will enjoy this, and thank you very much for listening to these lectures. So this is, as I mentioned, this is going to be the last exercise for the laboratory session. Thank you very much, and if you have any questions or if you want any clarification, please feel free to write to me, or you can write to the TAs, and then they will be able to help you. Thank you very much.
Welcome all. Today we'll be learning about self-priming monoblock pump, right? So you can have a look here. First, let me explain the nomenclature. Monoblock means single piece, right? There is the entire thing. For instance, you have a thing called monolithic structures, right? You go to, for instance, you have certain Ajanta and Ellora caves, you have in Mamallapuram, you have monolithic structures, right? Temple structures which is carved out of a single stone. So these are called monolithic, or in other words, monoblock. So in other words, these pumps don't have a coupling. The motor shaft directly is connected to the impeller, and the entire thing is what we call as a monoblock design. So we call these such designs monoblock design. Now today what specifically we'll look at is, we'll look at a pump that is self-priming. Okay, before we get into the pump, let me explain what priming is. So you might have seen when you install a pump for the very first time, right? You have to basically pour water into the pump. Why do we do that? Basically, we do what is called priming the pump. So why do we do that? So normally there are several types of pump. So this pump is placed above the water level, right? It may be placed at ground level or slightly above ground level, and the pipe that is connected from the pump to the water source, that is called the suction head, right? That length of the pipe, that height is called suction head. So, or the suction line. So this suction line normally has air in it. So these pumps are what is called non-positive displacement pumps, right? They cannot suck air. They can only suck a medium such as water. So something that is slightly more denser. So the design allows them only to handle water. They cannot, normally what we call the centrifugal pumps that you have, cannot or non-positive displacement, or in other words, the centrifugal pumps cannot suck out air. So you have to basically fill the suction line and the impeller casing with water, and then make sure you have a foot valve at the bottom of the suction line to basically hold that water column when the pump is turned off, such that whenever you start the pump, up to the impeller casing, it is filled with water, and there is no what is called air lock in the system, at least in the suction side. Delivery side need not be filled with water, it can be empty. So pump can basically pump water above the impeller, above the volute casing. But today we are going to look at a special type of a pump. So this is a pump wherein you don't have to basically fill the entire suction line with water. It is only enough that you fill this portion just by removing this. So you just have to fill in only this casing, just maybe half a liter of water you pour in. So you have a separate provision for that. You open this, you put a funnel, and then you fill it with water, only this portion. So this is the suction line. So basically you can see the arrow that is marked inside. So water goes inside the pump this way and it exits the other way from the top. So let me just remove this. Okay. So this is what we call as a flange. So basically so it is threaded. So there is a female thread here. So basically we will connect a pipe here. This is a pipe thread, national pipe thread, NPT thread. So it is a taper thread which is self-sealing. You don't have to, you only have to apply a sealant, and then when you screw in the pipe, it is self-sealing. So the thread has a taper to it. If you observe carefully, there is a mild taper to it. So that provides sealing between the pipe and the flange. So again you have what is called as this is a non-return valve. Okay. So when you assemble this, so you saw that it was placed this way, right? So this pump has not yet been installed. So it is important that you flip the non-return valve and then put it this way. Reason is, so non-return valve or check valve can only allow flow of water this way, in this way. So when there is a pressure differential, this is differential pressure operated, right? It opens by itself due to pressure differential, and then it opens this way. If I wrongly put it this way, what will happen? It will try to suck water, but water cannot go this way, it can only go this way. So pay attention to the direction. So the valve has to be placed this way. Okay. So this is a non-return valve that basically ensures flow of water is only one way, not the other way around. Now let us continue dismantling it, right? So right. So this is the casing. So as you can see, so there is a wall separating it. Water enters this way. You can see my finger come out this way. So look at the direction of rotation. So it goes counterclockwise. The impeller rotates counterclockwise. The impeller rotates counterclockwise. So this is a special impeller. So these impellers you will only find in self-priming pumps. Okay. So water enters this way. So it basically enters tangentially here, right? So impellers carries the water. So remember this entire top portion and the casing is filled with water, and then it goes around and then exits and then comes out through the top. So basically you can see there is a wall separating here. So water enters this way. You can see my finger here, comes around the annular region, and then again, so it enters little bit tangentially, right? And then again enters tangentially out little bit. Not strictly tangential, but in a kind of it's almost tangential. So the feature of this thing is, by continuously circulating the water, little by little the pump will evacuate the air that is there in the suction line. So after you run the pump for maybe a minute or so, the water will keep circulating and slowly it will suck out the air, and then water, because it is dense enough, will keep falling. So water will not be discharged initially. So once the entire suction is fully drained of all the air, now it is filled with water, the pump now basically has primed itself. So that's why we call it as a self-priming pump. In case of a centrifugal pump, what we have to do is we have to fill something like, depending on the length of the volume of the suction line, you may have to fill something like 15-20 liters of water depending on how long it is. In this case, because of the design, it allows just to fill a very little quantity of water and the pump self-primes itself. So this again, if you look at it, this doesn't have what is known as a volute casing. So you can see the casing more or less it's uniform throughout. In case of a volute casing, you will have a gradually expanding outlet. Please take a look at the construction of a standard centrifugal pump. It is called as a volute casing, V-O-L-U-T-E, volute casing. Again, that is pretty much to do with the impeller and the casing of the pump. So when you look at the motor, this is a standard. Let us look at the nameplate. The nameplate says it's a single phase 0.37 kilowatt 2-pole rated motor. Why is there a 2-pole here? Because we know from the other study that no single phase motor is self-starting. You always have what is called as a capacitor start and run motor. So basically you have two windings. Okay. Now you have a standard 10 microfarad electrolytic capacitor. These capacitors are called electrolytic. You can see. So it is filled with, so there is a coil of parallel plates that is in a coil form, and there is a dielectric that fills it. So this capacitor basically is connected to the starting winding, and then the other line, it's connected to the running winding. So basically you have two windings. So occasionally every 3 to 4 years you may have to replace the capacitor as it gets old. Now let me dismantle the blower that basically cools the motor. So you can see, so it is a common shaft. On one side you have the impeller, on the other side you have the blower. You can see the fins here are much larger because air is much less denser compared to water. So this handles a much more denser liquid. This on the other hand handles a much more less denser fluid. So basically this is again a centrifugal fan. So air enters axially, right? So if this casing were not there, what will happen? Air will enter axially and it will basically radially air will be blown out. Since I have a casing, what happens? Air enters axially, it is thrown out radially. The casing will again redirect the air again back radially, axially over these fins basically. So in operation, if you keep your hand here, you can feel the air flowing over the fins to basically cool the motor. Right? Now the entire motor casing, you can see it is made of aluminum, and if you look at the cross section, it is of uniform cross section. So typically the entire casing is extruded. You have a single die. So this will be one very long piece, and then basically they cut it into smaller pieces. So it becomes very, very cheap for the manufacturer to produce motors this way. Otherwise, if you were to cast it, you will have to basically create a casting for each and every motor that you need, and the fins cannot be this thin. So the thinner the fins, the more efficient it will be. So these are aluminum fins. We know aluminum is a better conductor of heat. So compared to cast iron, this is better, and it is thinner, and it is also thermodynamically very, very efficient. So I think the motor itself is what is called as a squirrel gauge motor. We've already looked at squirrel gauge motor in a table fan. Construction wise, it is literally the same as a table fan. So we will not have a look at it, right, Mother? So typically, so it will be the exact same thing, the squirrel cage motor as you have seen in a table fan. So I mean, construction wise, it remains the same. So other than that, that pretty much is all you have to know about a self-priming monoblock pump. So to summarize what we have learned today, basically we have learned about a self-priming monoblock pump that is basically capable of priming itself. In case of a normal centrifugal pump, a pump that is called a non-positive displacement pump. What is a non-positive displacement pump? Basically, the pressure is dependent on flow. In case of a positive displacement pump, pressure is independent of flow. So that's what we say. So if I were to basically stop the flow at the outlet, right, the pressure will rise up to a certain extent and will stop in case of a non-positive displacement pump. In case of a positive displacement pump, if I were to block the output, the pump will build pressure, and after a while, basically, it will depending on the motor, either the motor will stall or the pump itself will fail. So that is something to keep in mind. We all have a positive displacement pump within ourselves. It's basically the heart, right? Keep in mind, a positive displacement pump works by varying a fixed volume. How does a heart work? Basically by contracting and expanding, right? So it changes, it works by changing a fixed volume. So heart is a positive displacement pump. Why do we have a positive displacement pump? Because now I am standing, blood has to be pumped through all the veins in my body. There is a humongous back pressure that is there, right? This pump is a non-positive displacement pump, which means it cannot produce a very high pressure, right? Heart's role is to basically push blood through all capillaries and veins, which are extremely small in size, right? So which means it is working under a huge amount of back pressure. So a positive displacement pump is preferred there. And a positive displacement pump is self-priming. Keep that in mind. A non-positive displacement pump is not self-priming, but this is a special construction of a non-positive displacement pump. By way of construction of the impeller and the casing, we basically convert a non-self-priming pump into a self-priming pump. But nevertheless, remember, this is again a non-positive displacement pump, which means if I basically cut the output, it will develop pressure only up to a certain point, and it will simply be circulating water there. So it cannot build pressure beyond a certain point. So it has limited applications. But what is the good thing about it is if I were to cut the output, the pump has some level of tolerance built into it. For instance, if there is a block or a clog there, the pump will not destroy itself. So it is ideal in a home use. In case of a non-positive displacement pump, if the pump's delivery were to get blocked for whatever reason, it will basically, the pipe will blow up, or the motor will basically stall and the coil will burn. Something will basically go bad in case of a non-positive displacement pump, in case of a positive displacement pump. Again, one more thing to remember is, in case of a non-positive displacement pump, it does not work by varying a fixed volume. The volume is fixed. The casing's volume is fixed. We have an impeller that basically rotates and creates a suction, right? In case of a positive displacement pump, it creates suction by varying a fixed volume. So this is something you have to keep in mind. I hope you found that informative. Thank you.